In this video, we are going to be showing how a Maxwell-Stefan equation relating the velocity components of a system can relate to the molar diffusive of a system. Or can relate to the molar diffusive fluxes of a system. So, I've already written the velocity components of this Stefan-Maxwell equation. So I'm going to show how we can slowly convert this into diffusive fluxes with some equations that we've used in the past. So we have the driving force of our system, and what I'm going to first do is I'm going to try to convert the velocities into our molar fluxes for our system because we need molar flux to solve for diffusivity. So the way that we can do that is we can take one of our past equations uh, that relates velocity by saying that concentration times the velocity of a component equals the molar flux of that component, right? And so what we can do is just multiply the numerator and the denominator by some concentration. And when we do that, we should get something like C multiplied by x of I to V, which oops, then turns this into molar flux times the molar fraction minus n of j, x of j. It's supposed to be j there. And then we can put this over the concentration times the diffusivity of our system. And now we can put the sum of n, j equals 1. So now this looks like a different step in Maxwell equation. And this is sort of the intermediate step before diffusivity. I was saying that you need molar flux to solve for diffusivity, and that's because the two relate to each other with the molar flux equation. If we plug in n of I in this case, the molar flux equals a diffusivity plus some concentration gradient, which in this case is going to be the molar fraction of I times the concentration multiplied by the total molar flux. And so if we go ahead and plug this into the numerator, you can get something like n j equal 1. We get, let's see here, I multiplied by, oh, what happened here? Sorry about that. Sorry, I think this is a bit performance heavy on the iPad. Uh, been happening a lot with the previous parts of the assignment, so sorry about that. Right. So, okay. So we have 1 C of n. Okay, I see what I did here. Something like that. And then we're going to have this be subtracted by with y. N. And then it's going to be over some concentration multiplied by the diffusivity. Let's see here. Two. Actually, so this should be the inverse. So it does that. And now this turns into 5. And when we do this, you'll notice that we have like terms that we can cancel out immediately. We have the concentration gradients of each component, which actually cancel out in this case. So we can go ahead and remove them. And when we do that, we can now get our diffusivity Maxwell constant, or Stefan Maxwell equation. It's 1, which then equals x of 1, k1 minus xj. Diffusivity of, I think it should be that. And then this is over concentration multiplied by our diffusivity. Okay, so we've kind of shown step by step how the velocity component, Stefan Maxwell equation relates to the molar flux Stefan Maxwell equation by relating it to our molar flux equation. And then we did the same thing here, except we used the diffusion equation this time. Uh, Sorry, hold on. I'm getting mixed up here. Sorry. So we said that the concentration times the velocity of a system equals the molar flux of the system, and that molar flux is also equal to the diffusivity plus some concentration gradient, which in this case, this was a molar concentration gradient. And we did that to then prove that this equals some molar diffusive flux, Maxwell-Stefan equation. So that's what we were proving over here. So to explain the Maxwell-Stefan equations, uh, or I should say to explain the reference chemical potential as the pure state and showing how the Maxwell-Stefan equation, uh, or showing that the Maxwell-Stefan equation's driving force for a one-dimensional problem related to this is just a derivative of the mole fraction, um, with respect to some coordinate, we have to look at chemical potential as an equation, which we will something like this. Function. So all this is saying is that we have for our actual chemical potential, we have to start with some standard or the beginning of a chemical potential equation, and that usually these two are not the same. So that we need some comparison that actually considers a gas law in this case in regards to some mole fraction and temperature to then allow us to actually find the chemical potential of a mixture. And so what we're going to do is we're going to put this as the problem states in a one-dimensional problem. And we're going to put this in the y direction. And what I'm also going to say is that uh, our reference chemical potential equals 0 in this case. So we're starting from nothing. And so when we do this, we get something that looks like this. Chemical potential or some distance equals gas law times temperature multiplied, and then we're going to take the derivative of this. And when we do, we get 1 over molar fraction of whatever molar fraction of our first component. And we're going to multiply this by the derivative of this component multiplied by d of y. So now what we need to do is I'm going to actually go ahead and take our diffusivity Maxwell-Stefan equation that we had got from the previous part and show how this subs in. So I'm going to go ahead and copy this down. So our driving force in this case is going to look a little different. Our driving force is going to look like this equation. I'm going to write this as 1 over RT, and this is going to be multiplied by, let's say in this case, it's going to be our chemical potential in regards to some distance, and then is multiplied by some mole fraction, right? So something that you should see is that we have a like term here. Chemical potential is some distance over here and here. And we have units that should cancel out over here. And so what we can do is cancel out gas constant and temperature and our mole fraction. And when we do that, all we're left with, let me go ahead and erase this. All we're left with is the mole fraction in regards to some distance. Now, we did that because what this shows is that, oh, wait, I think I actually wrote this wrong in the previous part. Sorry. This is driving force equals the sum. That is my bad. So let me write this over here too. And 1 equals, and then this is a fraction in regards to some distance. Okay, so after subbing in the equations with the Staffel-Mixon equation and using the chemical potential as a driving force, we were able to prove that, in essence, that for a one-dimensional problem with some direction, which we said that this is the y direction, that the derivative of the molar fraction with regards to some distance is actually the driving force for the Maxwell-Stefan equation by subbing in the values into the Maxwell-Stefan equation. This is something. Okay, cool. Okay. So we have our diffusivity equation with Maxwell-Stefan equation. So what can we do with this equation and actually turn it into Fick's law? So something that I'm going to do, which is going to seem strange at first, is I'm just going to say that I equals 1. And we're going to proceed uh, until it equals 2, right? So when I first do this, we get x of 1, j of 1, minus x of 1, j of 1 for a concentration diffusivity of 1, 1. This seems stupid, right? Because we just got 0 out of this, so that doesn't really do us anything. However, if we proceed with this, if let's say that j equals 2, what we can get, oh, did I flip these? Oh, I very well may have flipped these. This is supposed to be j. This is supposed to be I. Sorry. I think I copied this wrong. Do something like that. And so now we should get something like j of 2. And then this should be minus x1, j1. Oh, wait, no, no, no. This is x2 and then j1. That's what we should have. Sorry. And then this is over the concentration and diffusivity of 1, 2. Okay, so now we're gonna do some pretty basic thermodynamics really quick. We're gonna say that for the sake of simplification, that our mole fractions are equal to 1 equals molar fraction 1 and molar fraction 2, right? And that our diffusivities of J1 plus J2 add up to, oh, goodness, come on, work with me here. Sorry, this iPad is trugging along. J2, right? So what we can do is simplify this equation. Just gonna fall it off over here. And I'm going to put it in terms of x1 and j1. So we have x1 equals, this would be j2 equals negative j1. So this would be negative j1. And then this would be minus x2 equals 1 minus x1. So this would be 1 minus x1. And then we would do this with x2. Oh, wait, no, and then we'd multiply this by j1. So when we simplify the numerator, we get x1 negative x1 j1 plus x1 j1 minus j1. And if we look, that cancels out. So we're left with just negative j1 over c d of 1, 2. Also, I'm saying j a lot. That's diffusivity. Don't worry. I know what I'm talking about. I'm not a fool. So this is awesome because if we remember Fick's law, Fick's law equals concentration, diffusivity along some gradient of molar fraction, right? Which let's just do this in a y direction for simplification. So this is great, but we're missing the concentration gradient part. So how do we get that? Well, if we remember from our previous part, our driving force is our molar fraction. So I'm just going to put our molar fraction over d of y. And now this looks pretty straightforward, right? Because now we're just going to say that j of 1 equals negative c diffusion of components 1 and 2 multiplied by the molar fraction over some gradient, right? And now we have fixed law because we use the diffusivity equation that we solved for in part one, and we use the same driving force that we solved for in part two to prove that when you combine the two together, you can simplify it by assuming two components where you have one one and one two, and using these molar fractions and diffusivity rules, or just basic addition, to then simplify the equation total into fixed law. So now this last question kind of just asked what is the relevance of Maxwell-Stefan equations. So this is kind of the my thermodynamics professor put it in a pretty like simple way. Maxwell-Stefan equations are kind of what grown-up engineers use. When you start off in the beginning years of chemical engineering in particular, they'll always use ideal gas law. And it's very convenient. It makes for very simple equations that give relatively good results in low pressure situations. But the critical thing that they don't account for is intermolecular forces. They don't account for the fact that gas particles do collide. They hit each other sometimes, and that can cause interactions which can either increase or decrease pressure. You may have retrograde condensation, which means that when your pressure goes down, you somehow have more liquid, which can seem confusing at first, but it's because of intermolecular forces interacting with each other. And that's kind of what Maxwell-Stefan equations take into consideration. They consider the molar flux, they consider the diffusivity, and they allow us to easily scale other Maxwell-Stefan equations with another Maxwell-Stefan equation to figure out different results. We were comparing the velocity components of a system to now comparing the diffusivity of a system just by relating them to some molar flux diffusivity. So they are very relevant equations, both for theoretical study and for actual real application. So I would say that is probably the relevance and application of the Maxwell-Stefan equations.